All right, so here's a fourth example in class 20 for Newton's second law applied to rigid bodies. This comes from Schaum's outlines right here. So they got this, we have a two-parter thingy with a ball, a sphere, I guess, and a rod. And the sphere is 100 kilograms, and it's rigidly attached to this rod that's got a mass of 20, and it's in the horizontal position so that like gravity is working downwards, just so you know. So it's in the vertical plane. They should really try to say that too. Determine the magnitude of the angular acceleration of the system and the reaction at O of the rod. So if we want to find the center of mass, there's a couple different things here that we could probably have done. But we take 20 and the location of the center of the mass of the rod is at 0.3 meters, so that we end up with 6 is that mass times that distance, and the rod is, no, the sphere, sorry, is 100, and the distance is 600 plus half of the 300, or 0.75 meters. We end up with 75, so we end up with 120, and then we end up with 81. So if we take the sum of the masses times the distances and the sum of the masses, we end up with 81 divided by 120, or 0.675. So it ends up actually the center of mass is somewhere like right around there somewhere. That's in meters, by the way. And if we want to try to get the mass moment of inertia right here of the rod, let's see, we get 20, and its distance, or its length, I should say, is 0.6. So we take 1/12 mass times L squared, or 1/12 20 times 0.6 squared, and it ends up with 0.6, which is a very big number. And its distance from that to the pin that we're going to move it is going to be 0.3. So we take 20 times 0.3 squared, and we get 1.8, and then we add those two things together and we get 2.4. We do the same thing for the sphere. Its radius is 0.15. We look up for a sphere, which we might not have in a standard table of these, but we will find that a sphere's mass moment of inertia about its center is 2/5 mr squared. So 2/5 100 are 0.15 squared, and we get that's going to be 0.9, not a very long number. The distance it needs to move to get to that pin O is 0.75, so we take the 100 times the 0.75 squared, and it ends up with 56.25. So we add this I together with the parallel axis theorem movement, the m times the x squared, and we'll see that it comes out to 57.15. Something notable here, and one of the reasons I kept it separated like this, is you can see that the distance that it moves has so much more of an effect of its actual own mass moment of inertia. It's that distance that's causing, especially the distance of that sphere, really is, and that combined with the fact that it's 100 kilograms. So we end up with 59.55. And these are the way the kilogram meter squared are the units. So if we draw up the FBD and IBD of this, I didn't give myself a lot of room here. Move it over. We could do this a couple different ways. I think I'm going to do it in both ways. Okay. So we have the this thing acting at the center of mass. which is going to be, a lot of times I'll write weight. Sometimes I'll put mg. Quite often when it's metric, I'll put the mg over here. But if they already gave me the weight, I'll write something else. The reactions. I think here I'm going to make them a positive direction right here. And so that's going to be the ROX and the ROY. So make them reactions. And then for the accelerations here, we actually have accelerations here and acceleration there. And then angular acceleration. Oh, and it is moving. So it's got an angular acceleration, I'm going to guess, is in that direction. I think so. I'm also going to have an omega right here. So I'm going to have the mass times acceleration in the x direction and a mass times acceleration in the y. Nope, I said x wrong. In the x direction and in the y direction. And by the way, I know that the acceleration in the x direction is actually going to be the normal acceleration. So it's going to be omega times the x squared. Right? No, yeah, omega times x. No, omega squared times x. Sorry. And that distance right there is actually that x bar, right? And I should have written x bar right up in here. And I know that the acceleration in the y direction is going to be equal to the tangential acceleration. So that's going to be alpha, and that too is going to be x bar as part of this if I wanted to get that. So here is going to be, this is actually a different approach, or something that I should mention. We want to be careful that we never combine or do a double dipping in the sum of the effective moments, right? That we can, excuse me for a second. The effective moments idea is only when we're dealing with about the center of, am I going to say that correctly? All right, so we have a choice here. We could either write the sum of the moments is equal to I-O times alpha, right? Or we could say the sum of the moments about G is equal to the sum of the effective moments about G, right? So let's do it this way on the left first, right? I really go into this in more detail in the next class and really try to hammer home right here. So I'm almost hesitant to include this example here done this way. We might want to like hold off on it and do it the way that's on the left right here, so that we can make that distinction. On the left, I'll continue anyway and write it in light blue. We write this. We could say that the moments on the right hand side about this are going to be a negative mg. So that's going to, the total mass is 120, and the gravity is going to be 9.81, right? And the distance that the moment arm is going to be that 0.675. The mass moment of inertia, and this is going to be a negative right here, is the thing that we calculated, 59.55 alpha. What we end up is getting the alpha of this is 13.34 radians per second squared. And that's going to be clockwise. The alternate method that I describe over here, right, this guy, I'll show you why this is another way to do it, right? But this is actually the way that we've been doing it so far in this class, right? That we're using the effective moments. So let me redraw out for this explanation. We have a free body diagram and an inertial body diagram right here, right? But let's just take these as parts, right, that are connected to each other, yes, but they're individually, they have their parts. And so writing it out that way, well, let's see, put the reactions in there. Reaction here, reaction here. So this is ROY and ROX right up in here. And I didn't finish the rest of that because they wanted the reactions, but we can get those another time. This is more important. We will put in the weight or mass of, I guess, did I give it a designation of a rod or something like there? I guess I decided to call this the rod A and the sphere B. Or did I call it a sphere? No, I called it just B. And then the same thing over here, but we're going to have mass of A times acceleration of A in the y direction, mass of A, acceleration of A in the x direction, and then we're going to have I of A bar and acceleration times the angular acceleration. And all the same things over here, but for B instead. MB, AB, Y, and then kind of hard to fit in there. MB, AB, X, and then this guy. IB, alpha, B. I should have done this one first, probably. Done it this way, just to demonstrate the thing. But some kinematics that we can that we can handle right here is that we know that the acceleration of A in the y direction is going to be equal to alpha. And by the way, we know that alpha for the whole thing, that alpha A is equal to alpha B, the rigid body, it has to be the same thing everywhere. So we'll just call this alpha, and it's going to be times the distance, or R A with respect to O, right? It's going to be this distance between here and here. And that ends up being alpha times 0.3. And then the acceleration in the x direction is going to be omega squared, and they both have the same omega, and that's going to be also be RAO right here. So it ends up being we actually know this is 8 squared times 0.3 or 19.20 meters per second squared. The same thing for our B right here. We could find that was A. The acceleration of B in the y direction is going to be alpha R B with respect to O, which is going to be alpha, and that's 0.75 if you'll recall. And for B in the x direction, it's going to be this omega squared RB with respect to O, or just 8 squared times 0.75, and it ends up being 48. And I think I wrote the wrong thing on my page. That's okay. 48.00 meters per second squared. And so now if I take the sum of the moments about O and make them the sum of the moments of O effective, right? So I think I lied to you when I said it was G down here. It should have been O. What we do is we say, we take a look at each of them, and counterclockwise is positive, so we go negative MAG times RA with respect to O, right? So this is the moment arm that moment, that force passes through. Then minus MB times G R B with respect to O. So this is the moment arm that passes through. It's going to be equal to all the things on the right-hand side, which I think I begin with I of A times alpha. Okay, that's alpha A, but that's the same. Alpha A is equal to alpha B, so it's just alpha. And then take minus MA AAY, but then you also need to make it into a moment. It's an effective moment. We want R times A with respect to O. I'm going to run out of room here. And then we also have IB alpha, and then we also have minus MB ABY RB with respect to O. So if we put all those values in here, we get minus 20 times 9.81 times 0.3 right here. Wow, it's really going crazy in that thing. And then minus 100, 9.81 times 0.75 equals I, which I don't know if I got that individually, right? Yes, I did, right here. 0.6 times alpha, and then minus 20 right here. This guy right here we got from up here, right? Times alpha 0.3, but then also times 0.3 again. So it ended up being 0.3, I guess 0.3, so that's how I wrote it down here. And then minus IB, which was 0.9 alpha, and then lastly minus 100 times the alpha 0.75, but then again times 0.75 squared, and we end up getting an alpha of 13.34 radians per second squared clockwise, which is the same thing that we had up above. The point here is that what we did when we came up here and found the mass moment of inertia about O was we did the parallel axis theorem, but right buried inside here is the parallel axis theorem. Right here is the parallel axis theorem for this bar, and right here is the parallel axis theorem for this sphere, right? Where, and I don't know why I put them on that side. We could almost put them over on this side, right? That we took the mass moment of inertia about its center, and then we took its mass times the distance it moves squared, and both of them were times alpha. And the same thing here for the sphere rotating on its own, and then for the mass times the distance again. So there's the parallel axis theorem. So we could get the same result doing either way. It's probably a really long-winded way of pointing it out. And then the reactions that you get would just be the sum of the forces in the x direction. And in that case, we get that omega r right here squared. So we get the omega squared r, I'm sorry. And we end up getting that acceleration, and we're able to get what the reaction forces are, because it's the only thing going on in the x direction. And we notice it's to the left right there, so that's what we're end up getting as a solution. And the sum of the forces in the y direction, we note that we have the weights to contend with, and we get the normal force there. So I just think it's important to, the most important part of this is that we have two different methods of finding it. We could either get this right here, where we can go ahead and take the mass moment inertia about the point that we're working on, or we could take the individual parts and take it about O, and we'll see that it ends up being the exact same thing.